on behalf of Automobile Department, our HOD sir, all my colleagues, we welcome you, sir. Sir, please stay for some time, sir. The participants now they are fastly joining your presentation, sir. Once our HOD sir has arrived, uh, in formal way, we'll start our presentation, sir. Thank you, sir.
Ms. Bani Darbashatu, can you stop presenting your screen? Click on stop presenting. Bani. Bani Darbashatu. Click on stop presenting. Thank you.
Rajagar, how are you, Rajagar? Good morning, Rajagar.
Shyam? Mr. Shyamvel?
Sir, good morning, sir.
Very good morning, Pa.
Yes, sir. Sir, so far we have reached 173 participants, sir.
Okay, Ma. Expert joined the meeting?
Yes, sir. Yes, sir.
Yes, sir. Already he is in meeting, sir.
And sir, welcome.
Yeah, good morning. Welcome. Thank you.
Oh, welcome. Fantastic. Shyam, we can start the presentation or we just wait for another 2 to 3 minutes? Right?
Sir, now as of now we got 180, sir.
Okay.
Still people are joining, sir.
Okay, okay.
Shall we wait for another some 2 or 3 minutes, sir?
Fine, Ma. Fine. Fine.
Yes. Sir, we have reached around 205 participants, sir. If it is okay, we can start, sir.
Yes, Shyam. We can start, right?
Yes, sir. Yes, sir.
Yes. Sir, Dhamodharan, sir, shall we start our session, guys?
Yeah, sure.
Great, sir. Dear participants, very good morning to all. On behalf of Hindusthan College of Engineering Technology and Department of Automobile Engineering, welcome all the participants who are all joined here for this great occasion. It is a 6 days FDP on nanomaterial synthesis process characterization and its functional application. And also, I extended my warm welcome to today's chief guest, Mr. Dhamodharan. Before I hand over the session to Mr. Dhamodharan, I'd like to give a brief introduction about Mr. Dhamodharan. He has completed his BSc in KSK College of Arts and Science in University of Madras, and he has completed BTech in Dr. MGR Educational Research Institute, Chennai. And after that, he is joining MTech in Anna University, Chennai, and he went to PhD for Fujian Institute of Research on the Structure of Matters, Republic of China. And he has a lot of experience. He has published a lot of journals in the area of polymer nanocomposites, and he has received honors and awards from various funding agencies. Especially in 2017, he went to Fuji Institute of Research and Structure of Matters, China, for the travel grant for the research doctor for doing a research doctorate degree. And 2017-18, he has received a fund of National Engineering Research Center for Optoelectronic Crystalline Materials, the STS project of Fujian CAS. And 2017, he has received the award of University of China Academy of Science, Chinese Government Scholarship Fellowship. In 2019, he has completed his doctorate in University of China, and it is the excellent international student nominee of Fujian Institute of Research on the Structures of Matters. With this short profile, I welcome Dr. Dhamodharan to give an insight presentation to the participants. Welcome, Dhamodharan, sir.
Thank you, sir. Thank you.
Fantastic.
So, shall I start my presentation now?
Yeah, yes, sir. Yes, sir. We are all
Okay. Thank you.
waiting, sir.
Thank you. Thank you. Can everyone able to see my slides?
Yes, sir, we can see, sir.
Okay, thank you.
Yes, sir. Yes, sir.
So, before I start my presentation, I would like to welcome you all for my presentation today, and I would like to say my sincere gratitude to the Hindusthan University to arrange FDP for faculty. Those on this critical situation, people, experts, they cannot meet together and they cannot share their experience. But fortunately, like Hindusthan University, they have started an online FDP program to share our knowledge to help each other. So on this behalf of Hindusthan University, I welcome you all for my presentation today. So today my presentation is related to graphene oxide based waterborne epoxy nanocomposites. So before I start, actually I just want to tell you some related to my project. Actually, this is why I work with waterborne epoxy. Nowadays, people, we all know that polymers are attracting great significance in our human being life, because if you take any material in home or anywhere in the industry, most of the materials are made by polymers. So while we using polymers, what will happen? Most of the polymers are solvent-based polymers. So while we using solvent-based polymers, during curing process, the lot of volatile organic compounds will evaporate. So these volatile organic compounds are very carcinogenic to the human being as well as the environment. So what we plan to work, we want to just find a better replacement for the solvent-borne epoxy. So that's what we work with the waterborne epoxy, because waterborne epoxy is having very less VOC, and also it is very easy to handling, and great difficulties. It has very less mechanical and thermal property as compared with the solvent-borne epoxy. So what we plan, so we want to enhance the mechanical and thermal property of the waterborne epoxy. So here what we work with the graphene oxide, because graphene oxide, we all knew that graphene oxide is having large surface area and its mechanical and thermal property is extremely high, and also it has lot of functional group on the surface of the graphene sheet, so it can able to make better covalent bonding between our waterborne epoxy, then make a better property. So before start my project, I plan to give some short introduction, but fortunately professor gave my short introduction, so I just skip these slides. So here is the outline. So why we have taken waterborne epoxy and why graphene oxide, and also what I have done. This is the outline. So this also I explained. So background. So initially I explained to you why we are what we are using, because polymer utilization around the world is increasing because of its outstanding mechanical and thermal property. And also the solvent-borne epoxy is having more volatile organic compounds too. These are very carcinogenic to our environment and as well as the human being health. So the curing process makes a lot of time, and also it need high temperature to cure better product. And also the final product is not easy to make without high temperature. And though polymers having high mechanical thermal properties, some limitation, I mean some utilization, some unplaced characters are limiting this utilization. So what we plan, so as I explained to you in the initial, so we plan to find a better replacement for the solvent-borne epoxy. So here we work with the waterborne epoxy. As I told you, waterborne epoxy is very less cost as compared with the solvent-borne epoxy, and also easy to handling and environmental friendly, but it has very low thermal and mechanical properties. So because the during curing process, a lot of micropores will form, because when we compare with the solvent-borne epoxy and waterborne epoxy, uh, water content will be very high in the case of waterborne epoxy. So what will happen during curing process, all the water molecules will evaporate, then there is a lot of micropores on the surface of the polymers. So to overcome those micropores formation, we plan to incorporate some nanofillers. So in this case, we just work with graphene oxide. So why graphene oxide? Graphene oxide is a sp2 carbon atom and 2D structure, and lot of oxygen functionalities on the surface area which can easily disperse GO into the WEP system. Yeah, WEP in the sense waterborne epoxy, and also GO showing a remarkable mechanical and thermal properties like graphene sheets. GO is having large surface area, supported oxygen functionalities which can able to make a better dispersion, followed by a covalent bond formation with our matrix system. So that's what we just used waterborne epoxy. And also in our waterborne epoxy we will use some curing agent. Here we have been used amine based curing agent. In the sense, amine based curing agent means at the end of the curing agent we have a amine functional group NH2. So those NH2 can able to make formation with the covalent bond formation with the graphene oxide. So graphene oxide surface generally will have oxygen, carboxylic and hydroxyl, carboxylic and epoxide groups on the surface of the graphene oxide. So for our project, what we have done in our laboratory, we will synthesize graphene oxide in our laboratory itself. So for that we have used modified Amherst method and Amherst method. So based on the Amherst method, we just taken 1 gram of 300 mesh graphite sheet. 300 mesh graphite powder we have taken. Those graphite powder has been mixed with hydrochloric acid, sulfuric acid to disperse initially. Then with the assist of potassium permanganate, we have prepared graphene oxide. But generally this graphene oxide synthesis is very dangerous because it is highly explosive. So we need to maintain the temperature less than 5 degrees Celsius. Later we need to maintain for 6 hours. After the 6 hours, we need to add distilled water 200 ml to increase the to provide the oxygen functionalities on the surface of the graphene sheet. So this process will be continue for 10 hours. After the 10 hours, we need to stop the reaction. So we have been used hydrogen peroxide with 80 ml hydrogen peroxide and 50 ml DI water to stop the synthesis of graphene oxide. Then later we need to keep for a settling process for a minimum 1 week, and we need to replace the water for 2-3 times to get a better explanation of the graphene oxide. So so what we found that generally when we work with a graphene oxide it's on its possible nature of getting agglomeration. So what is agglomeration here? So the graphene sheets are layer by layer structure. So this layer by layer structure, each adjacent layers, they have a van der Waals force of attraction between adjacent layers. What will happen if we keep the graphene oxide simply, the graphene oxide sheets will get agglomerated. Restacking, then it will be a bulge. It will become agglomerated. So once it will become agglomerated, we cannot get a better property because it cannot able to make a better bonding formation with our matrix system. So that's what we plan here. So we want to decorate our graphene surface to increase the interlayer distance between the each graphene oxide sheets. So in my first project, what we have did, I just decorated a graphene surface with a magnetite nanoparticle. So for the magnetite nanoparticle synthesis, I have been used, ferrichloride hexahydrate and ferrichloride tetrahydrate. So with the assist of, this is a precipitation process, so it is in situ process as well. So we have prepared our magnetite nanoparticle separately for better understanding how the mechanical property and thermal property has been increased with the incorporation of mechanical magnetic nanoparticle incorporation with our WEP system. And also the graphene surface also has been decorated with the magnetite nanoparticles to check the better anti-corrosion property between the magnetite nanoparticle and also the WEP system. What we come to know, when we decorate our graphene oxide sheet with a magnetite nanoparticle, generally graphene oxide is having hydrophilic in nature. But when we decorate our magnetite nanoparticle on the surface of the graphene oxide, so what will happen? All the functionalities, I mean, most of the functionalities present over the graphene oxide has been replaced by the magnetite nanoparticle. So what will happen here? It is not easy to dispose in water, and also our source material is waterborne epoxy, so it has to dispose very well with our matrix system. So when we decorate our magnetite nanoparticle with our graphene oxide, what will happen? Hydrophilic nature will become hydrophobic, so it is not easy to disperse. So what we plan here, we introduce some diol groups on the surface of the magnetite decorated graphene oxide. So for that we have been used MPTPMS. So with the assist of MPTPMS, 3-mercaptopropyl trimethoxysilane, it is a silating agent, so it will give us thiol functionalities on the surface of the magnetite graphene. So here we can see the graphical image schematic illustration of the whole synthesis process. So initially we have taken a graphite sheet, and with the assist of oxidation and sonication we have prepared a graphene oxide. The as prepared graphene oxide undergoes modification and co-precipitation process with the assist of ferrichloride hexahydrate and ferrichloride tetrahydrate. We have formed magnetic nanoparticle decorated graphene oxide. We can see here most of the oxygen functionalities has been replaced and the magnetite nanoparticles has been decorated. When you go for I will show you the results for characterization. We can easily understand how it is decorated. And after the stirring and sulfonation with the MPTPMS, we have got sulfonyl thiol group decorated magnetite nanoparticles decorated graphene oxide. So after the successful synthesis of the nanofiller, what we need to do, we need to incorporate that as prepared nanofiller with our WEP system to check the mechanical and thermal property. So here we can, initially we just mixed, disposed with our as prepared nanoparticle with the curing agent, with amine based curing agent to make a better bond formation with our WEP system and also the as prepared nanofiller. So after the curing agent mixer, then we have disposed with our WEP matrix with the assist of mechanical stirring, then later degassing and curing at 60 degree for 24 hours. And this structure is for mechanical testing. It is ISO standard. And so as I told you, whenever we prepare some nanofiller, we are supposed to characterize to quantify the quality of the as prepared nanofiller. So initially we have did structural arrangement, crystal structure nature by XRD analysis. So as prepared GO shows 8.6 to theta value. Generally graphene oxide should come less than 10 to theta value in the XRD. If it is comes less than 10, it is somewhat good graphene oxide. And in the case of magnetite GO and supported by diol functionalities, here you can see the 2 theta values are around 30.21, 35 and 43, 53, 57. These are belongs to magnetite nanoparticle peaks. But there is no graphene oxide peaks here because, as I told you already, graphene oxide surface has been fully overcovered with the magnetite nanoparticles, because that's why here we couldn't achieve the graphene oxide peak here. And in the case of FTIR analysis as well, so you can see the graphene oxide is showing 1629, 1400, 1225. Those are carbon peaks. And here in the case of Fe3 at GOSO3H, we can achieve, we have been achieved 584 and 445, which are related to metal ion peaks. So here we can confirm that our graphene oxide surface has been successfully decorated with our magnetite nanoparticles. So in the case of Raman analysis, you can see generally graphene oxide we will get D band and G band around 1300 and 1500. If we get this, it is we can conclude that our graphene oxide has been successfully created. And in the case of magnetite nanoparticle decorated graphene oxide sheets, there is no G band because G band related to carbon peaks, I mean carbonaceous structure. So here also we can confirm that our carbon structure has been fully overcovered with the magnetite nanoparticle. That's why here G band diminishing. G band is disappeared, and also we got 376 and 668 peak, which is related to magnetite nanoparticles. In the case of TGA analysis, we can see for the neat graphene oxide, we have got 38% residual value, but in the case of magnetite nanoparticle decorated graphene oxide, we have got 88% residual value. It shows that our graphene oxide surface has been decorated, and also the thermal property, I mean the thermal resistivity of the graphene oxide has been enhanced due to due to decoration of magnetite nanoparticles. See here, it is very important, the morphology study analysis. So we can see the SEM analysis of GO. It is like layer structure, and also the layer structure has been very thick layer. But in the case of Fe3O4 figure B, you can see that dotted particles are related to magnetite nanoparticles. In the case of GO, we can see the layers by layer structure. We can see one layer, two layers, three layers, like layer by layer. We can see on the layer surface, we can see lot of dotted particles. And even the TEM analysis also, we can see the thickness of the GO sheets. But in the case of magnetite nanoparticle decorated GO, the layer thickness is very less, and also the dotted particles decorated on the surface of the GO. So after the quality checking by the characterization, so what we have did, we have done with incorporation, and we prepared a composites with the WEP system. We just find tensile property analysis with the assist of UTM machine. So here we can see the neat WEP is showing 10.51 megapascal, but in the case of GO, at the loading of 0.28%, the tensile property has been increased remarkably around 24.55 megapascal. When we increase the loading concentration, the tensile property has been gradually decreasing. It is due to, as I told you already in the initial time, graphene oxide have its own property of the getting agglomeration due to van der Waals force of attraction between the adjacent layer. So we want to get better property enhancement. That's what we decorated our graphene surface with the nanoparticles. So when we decorated our graphene surface with some nanoparticles, what we have achieved here, our tensile property has been increased remarkably as compared with the neat GO. It is we have got that 8.35%, 35 megapascal graphene, 35 megapascal tensile property at the loading of 0.28%. So the tensile property and the elongation at break has been generally when the tensile property is increasing, elongation at break will decrease, because when the material stiffness is increased, that elasticity will become less. So that's why the elongation break is decreasing when the tensile property. In some cases, for example, if we use some MOF or some covalent CU enhance that thermal property, I mean tensile will able to give absorb the energy, and it can able to extend, and also it can, the stress value also able to withstand. So these graphene oxides are sheet structure, so it is not having any micropore structure in that. That's why the mechanical property increasing, but the elongation is decreasing. So the same way we have analyzed the DMA analysis. So here we can see the neat WEP is showing around 1300, I mean 1.25 gigapascal. But when we added 0.28% loading of GO with the WEP system, it is around 1.5 gigapascal storage more or less. But the magnetite nanoparticle decorated GO with the WEP system is showing a 2.5 gigapascal storage more or less. The same way tan delta value, it is a glass transition temperature. We can see the glass transition temperature also increasing remarkably. Generally, glass transition temperature is nothing but the rubber state will become glossary state. When the changes between the rubber state and the glossary state is nothing but glass transition temperature. So we just want to check why the mechanical property is increasing and decreasing. So the trend has been achieved with the, trend has been quantified with the assist of fracture surface by SCM analysis. So here we can see the WEP has highly brittleness and lot of micropores on the surface. But in the case of GO, while we incorporate GO into the WEP system, for the 0.28% incorporation with the WEP, we can see some uneven cracking, but the proper nano homogeneous arrangement, distribution has been achieved, but the bonding between the nanofiller and the WEP system is not as much as good. When we go with the higher concentration, we can see some agglomeration as well. But in the case of magnetite nanoparticle decorated graphene oxide incorporation with the WEP system, we can see the homogeneous dispersion as well as the even cracking and also the rough surface. It shows that the better property due to the better dispersion and also the better bonding between the nanofiller and also the WEP system. So after the mechanical property, we have achieved with we have analyzed with the thermal property with an assist of thermogravimetric analysis. Here we can see the thermal property has been increased. The thermal property is not much effective, though when we compare with the neat WEP, it is somewhat good. The same way for GO and also the magnetic nanoparticle decorated GO is also showing the somewhat increased thermal property when compared with the neat WEP. So in addition, we have done with the thermal conductivity analysis. So the thermal conductivity analysis of the GO is showing better performance at the loading of 0.28%. So the thermal conductivity value was 0.235. Thermal conductivity for GO with the WEP. The loading of 0.28%, magnetite nanoparticle decorated GO with the WEP was 0.248. Though it is very less, but when we compare with the neat WEP, it is somewhat good. So here it is the reinforcement mechanism why our mechanical property and thermal property has been increased. See, we can see here before curing, the system in the nanofiller is not tightly bonding, tightly packed. After the curing process, the better interfacial interaction has been increased, and also the covalent bonding between the introduced nanofiller and also the WEP matrix. That is what we have achieved better mechanical and thermal property. So this is our second project. So in the second project also, we decorated our graphene oxide with some LDH material. We have taken zinc nickel LDH. So for the zinc nickel, this is also in situ process. We have taken a precipitation method. So for the zinc nickel LDH, we have taken zinc nitrate hexahydrate and nickel nitrate hexahydrate, followed by the, here we have been used urea solution for pH maintenance, and also the graphene oxide will become reduced graphene oxide. Here urea working as a reducing agent as well. So here we can see the schematic illustration. So the same like a graphite has been taken and to form a graphene oxide. Then followed by graphene oxide, we have taken the nickel nitrate and zinc nitrate with the urea solution to form a RGO zinc nickel LDH. Here RGO is denoted that reduced graphene oxide decorated with the zinc nickel LDH material. So here the same like my previous project, the graphene oxide surface, most of the oxygen functionalities has been replaced with the zinc nickel. So hydrophilic will become hydrophobic like my first project. So here also we plan to give some functional group to make a will become hydrophilic. So here we have been used APTS, so aminopropyl trimethoxysilane, and so finally this one, the APTS treated RGO zinc nickel LDH will become denoted as modified RGO zinc nickel LDH. So the same method which we followed for the composite preparation. And here also we can see the zinc nickel LDH decorated GO surface has been scrutinized with XRD analysis. So the despacing between the adjacent layer, it is like a 0.86 nanometer for GO. It is very good. And zinc nickel LDH, when we analyzed with the XRD, we have got 003 plane, 006 plane, 101 and 110 plane. But in the case of MRGO zinc nickel LDH, we have got that 002 plane for the reduced graphene oxide peak around 28 or 30 something, and other zinc nickel LDH peak also we have been achieved. So we can conclude that our reduced graphene, our GO has been reduced, and also the GO's reduced graphene oxide surface has been successfully decorated with our zinc nickel LDH. So even the FTR also showing that 483 and 690, which is related to metal ion peaks, and also 2930 and 2875, which is related to CH bond, and 1560 and 1050, those are related to carbon peaks. So here in the Raman analysis, we can see D-band and G-band. Generally, Raman analysis using to find the structural defect. So here, for neat GO, we have got ID by IG value is 1.03. Generally, when the ID by IG value is increased, we can conclude that there is some structural defect because of our nanoparticles. See, ID by IG value has been increased remarkably as compared with the neat GO, and this is 1.03, but in the case of modified RGO zinc nickel LDH is 1.17 ID by IG value. We can confirm that our GO surface, I mean RGO surface, has been successfully decorated with the zinc nickel LDH. So in the case of TG analysis also, we can see a better thermal residual value has been achieved with the assist of zinc nickel LDH decoration on the surface of the GO, and also the GO has been reduced. So in addition, here we have analyzed XPS as well to find the better successful decoration on the GO surface. So for the case of neat GO, we have got oxygen and carbon peaks alone. But in the case of MRGO zinc nickel LDH, we can found that, see here, the carbon peak has been remarkably reduced, and also we have got zinc peak and also a little nickel peak here. So the carbon peak is reducing because the zinc nickel LDH has been over covering the carbon surface. So that is why in the X-phase analysis, the carbon surface has been disappeared. And also the zinc and nickel peak is showing, zinc is showing a very high because we have taken a very high amount of zinc and we have taken very less amount of nickel here. And this is a convolution peak for the better understanding. And in the case of morphology study, we can see the GO is showing sheet structure, multiple sheet structure, and zinc nickel LDH zinc nickel LDH decorated GO is showing patches. It's like zinc nickel LDH is decorated on the surface like patches. So zinc nickel LDH patches. So we can see the GO sheets has been having lot of patches. Those patches are related to zinc nickel LDH, and the GO became reduced, so it is RGO. So for the better understanding, we have done TEM analysis with higher magnification, the particle arrangement on the surface of the RGO surface. So here we can see the better neat arrangement, I mean homogeneous arrangement on the RGO surface. The zinc nickel LDH has been successfully decorated. So the same like my previous project we have did with tensile property analysis. Here the same WEP 10.51, and when we go with the GO 24.5, but when we go with the zinc nickel LDH decorated GO with WEP, it is 29.55 at the loading of 0.28%. So this is very less as compared with our first project, I mean my first project, but when we compare with the neat WEP, it is far better. The same in the DMA analysis also. So GO is same like my first project, and the DMA analysis of the zinc nickel LDH and the 0.28% loading, it is showing around 1900 megapascal storage modulus, and also the tan delta value is also remarkably around 119, I think so. So the better mechanical property achievement was scrutinized with the assist of fracture surface analysis with the FESM analysis. So here we can see the fracture surface and high brittleness of the WEP, but here we can see the patches. Those patches are related to zinc nickel LDH patches. So in the case of 0.28% of the zinc nickel LDH decorated GO with the WEP, we can see the linear cracking, and also there is no agglomeration part. But in the case of other concentration, we can see the agglomeration and also the uneven cracking. In the case of GO, it is not even considered because it is showing a lot of fracture and agglomeration as well. So the thermal property also analyzed with the system TGA. So the thermal property of the neat GO, neat GO with neat WEP is 9.6 residual value. But when we incorporated GO into the WEP system at 0.28%, it is become 10.4. But when we go with the zinc nickel LDS decorated GO with the WEP, it is 11.1. It is very less, but when we go compare with the neat WEP, it is somewhat good. So the same like a reinforcement mechanism for the better understanding, because due to better interfacial interaction, because of homogeneous dispersion and the better covalent bond formation. And this is my third project. So this third project is related to zirconium phosphate, because in our first two projects we have mainly concentrated with mechanical and thermal property, because those all our projects are industrial projects. So our industry people, what they want to enhance, what they want, they will just tell our requirement, tell their requirement with us, so we will just work for them and we will just develop the mechanical and thermal properties. So in the third project, the industry people asked us to work with some anti-corrosion and also some fire resistant value. So what we planned, so for the case of zirconium phosphate, we found that it has better fire resistant, and also the zirconium phosphate is having a smectic nature. A smectic nature in the sense while curing, the arrangement of the nanofillers will become horizontal in layer, and so this horizontal layer will make a better shielding effect. So we plan that it will clearly it will surely inhibit the electrolyte entering into the surface of the polymer. So that's what we plan to work with the zirconium phosphate. And zirconium phosphate, not only zirconium phosphate, because zirconium phosphate is having very less surface area. So what we plan here, so we can take a graphene oxide, then the graphene oxide surface will become decorated with zirconium phosphate, means it has a large surface area. And also what will happen without zirconium phosphate, graphene oxide will not make a smectic arrangement, but when we decorate zirconium phosphate on the surface of the graphene oxide itself, it will become smectic nature during curing process. So here we prepared zirconium phosphate decorated graphene oxide, and this is a schematic illustration. So you can see same like graphite powder followed by graphene oxide with assist of MS method, and then in situ method we prepared zirconium phosphate decorated graphene oxide. Here we can see the method for the composite preparation. Here in this method we have analyzed mechanical, thermal, and also some other property for the which are related, which are supporting to the anti-corrosion and fire resistant. So for the anti-corrosion, we have taken natural salt spray analysis here. So the as prepared composites has been coated on the steel surface. This is A3 steel. We have been used to spray coating. So after the composite preparation, we have scrutinized with the assist of XRD. So we can see here GO 001 plane, and alpha zirconium phosphate also we have prepared in our laboratory for our research purpose. So the as prepared alpha zirconium phosphate is showing 002 peak and 110 and 112 peak. And generally the zirconium phosphate has been modified, or any chemical modification, 002 peak will reduce and 112 peak will increase. And also here the geo surface has been fully overcovered with zirconium phosphate. That's why there is no zirconium geo peak here. And also we can see the 002 peak has been reduced and 112 peak has been increased. So we can confirm, based on the literature, we can confirm that our geo surface has been successfully decorated with zirconium phosphate. And also the zirconium phosphate also modified, because zirconium phosphate is also like sheet structure. And this is FTIR analysis. So in the FTIR analysis also we can see some phosphate peaks and hydroxyl peaks which are related to hydroxyl. And in the case of zirconium phosphate GO, we have got phosphate peak and also the carbon peaks and also the hydroxyl peaks. So we can conclude that our GO surface has been successfully decorated with our zirconium phosphate. So same like Raman. So Raman ID by IG value is increased as compared with the neat GO for the zirconium phosphate decorated GO. So we conclude that the geo surface has been successfully decorated with zirconium phosphate nanoparticles. So in the case of TG analysis also, see we can see the increased residual value. So we conclude that the geo surface has been successfully decorated. So the XPS analysis also showing the same. Here we can see the zirconium phosphate is showing zirconium and phosphate peaks, including oxygen. But in the case of GO, we have only oxygen and carbon peak. In the case of zirconium phosphate decorated GO, the carbon peak has been reduced remarkably, and also zirconium and phosphate peak we have been achieved along with the oxygen. So we conclude that the GO surface has been fully over covered with zirconium phosphate. That's why here carbon peak is not visible. So SCM analysis morphology study is showing that GO is having a thick sheet structure, and zirconium phosphate nanoparticle is showing different structural particles. I mean, more molecules. It doesn't have a proper structure because it is we prepared. So we have some polyhedral structural zirconium phosphate nanoparticles. In the case of zirconium phosphate decorated GO, we can see the patches on the GO sheets. So those patches are visible in the case of TEM analysis. We have gone through the higher magnification for the better understanding of the zirconium phosphate nanoparticle. Here we can see the zirconium phosphate decorated GO. The arrangement of the zirconium phosphate nanoparticle has been very uniformly. So for the mechanical property analysis, we have worked with tensile strength property. So while we incorporate our zirconium phosphate with the WEP system, at the loading of 0.38%, we have got better tensile property around 17.05 megapascal. In the case of zirconium phosphate decorated GO, at the loading of 0.9, it is very less as compared with my first project. But though when we compare with the need WEP, it is somewhat good. And this is comparative analysis of tensile and elongation. So as I mentioned you already, when the tensile property is increasing, elongation gradually decreasing because of the stiffness matter. And this is FESM analysis fracture surface. So already we have gone through more fracture surface analysis with first and second project. So we have just taken 0.38% loaded fracture surface here. So we can see a lot of micropores on the need WEP, which caused is highly brittle and easy cracking. But in the case of zirconium phosphate decorated, we can see uneven cracking, some agglomeration as well. But when we go with the zirconium phosphate decorated, it is showing a even cracking, though it has some patches, but it is even cracking and rough surface even. So the DMA analysis shows around 1700 megapascal storage modulus for zirconium phosphate, and the zirconium phosphate decorated GO is showing around 1900. So in the case of tan delta is also increasing remarkably, but not much as impressive in like my first project. So here is the thermal property analysis. So the thermal property analysis is showing better thermal property because we are using zirconium phosphate. Generally, zirconium phosphate is having a high thermal property analysis. So that's why when we incorporated zirconium phosphate with the WP system, we have got around 19 residual value. And when we go with zirconium phosphate decorated GO, it is around 24 residual percentage. So in the same way, the thermal conductivity also increased remarkably. So when we go with the zirconium phosphate, it is 0.5. But when we go with zirconium phosphate decorated GO, it is 0.5. It is very high when we compare with my first two projects. And this is a dispersion study. So generally, the better mechanical thermal property or any property achievement, we need a better dispersion. So if the incorporated nanoparticles can able to achieve a better dispersion with the WP system, I mean with the matrix system, whatever we are using in the matrix, if the matrix system has matrix system and the nanofiller is having better dispersion, and it can able to give us better property enhancement, and also the better dispersion will able to make a better arrangement and better bonding as well. So here we can see the dispersion study has been analyzed with the assist of FESM and XRD analysis. So the FESM, you can see the need WP is without any nanopillar, it shows micropores. But when we go with the WEP GO, there is some agglomeration, GO patches. We can see when we go sharply, then we can see the patches on the surface of the polymer matrix. And in the case of zirconium phosphate, we can see the patches like zirconium phosphate bulge patches on the surface. When we go with the zirconium phosphate decorated GO with the WEP, there is no agglomeration and also the rough surface. We can conclude that the better dispersion, dispersion with the WEP matrix with the zirconium phosphate decorated GO can be achieved. And in the case of XRD analysis for the neat WEP, we have got around 10 to 30 broad peak has been achieved. When we compare with the other two, I mean GO WEP, zirconium phosphate WEP, the peak has been slightly towards to the x-axis, but in the case of zirconium phosphate decorated GO, it is exactly same like neat WEP. We can conclude that the better dispersion has been achieved with the neat WEP matrix with zirconium phosphate decorated GO. So this is adhesive strength and water uptake study, because in this project we plan to work with anti-corrosion and also fire resistant. Generally for this anti-corrosion anti-corrosion assessment test, we need to do adhesive and fire water uptake, because if the adhesive property is high, the polymer can able to attach with the metal surface very tightly. If the water uptake is very less, it can be able to shield the material, I mean electrolyte or any material enter into the steel surface. So for that purpose, we have analyzed this adhesion and water uptake analysis. So we conclude that we got the results like when the zirconium phosphate decorated GO with the WEP, we have got adhesion strength around 2.9 megapascal. As compared with the other two, it is very high. In the same way, the water uptake also for 14 days we have been conducted, and after the 14 days we got that 0.30% of water uptake only can achieved with the zirconium phosphate decorated GO with WP. It is concluding that the micropore structure and the sheet structure, I mean the smegmatic alignment of these as prepared and incorporated zirconium phosphate decorated GO can able to shield the electrolyte material enter into the surface, I mean inside the surface, because the sheet structure is shielding. That's why we are getting very less water uptake. And this is the anti-corrosion analysis by natural salt spray analysis. So here we can see for the neat WEP, after 24 hours the corrosion has been initiated, and 72 hours the electrolyte you can easily enter into the steel surface, the corrosion has been already done. And after 120 hours we can see a danger, I mean highly corroded area. So in the case of GO incorporation with the WEP, so here we have taken 0.38 percentage only, because we have achieved a better mechanical and thermal property at the loading of 0.3. So we plan to work with 0.3 because we conclude that the 0.3 weight percentage is a feasible weight percentage for the mechanical and thermal. So we plan to work with that because it will give us better property like. So in the GO also we can see the for the natural salt spray analysis we have taken 3.5% sodium chloride. We were spraying on the natural salt spray analysis. The sheets, the plates has been fixed on the instrument, and the salt natural, I mean sodium chloride salt solution has been sprayed continuously. So the corrosion has been initiated in the case of after 72 hours. After 120 hours, the corrosion has been, you can see the corrosion medium. And here in the case of zirconium phosphate, we can see it is somewhat good as compared with the GO, and also very good when compared with the WEP. So the corrosion has been after 120 hours, the corrosion has been somewhat it is prolonged, but not as much as with zirconium phosphate decorated GO surface, because as I told you already, zirconium phosphate can able to make a smegmatic alignment, but the nanoparticle surface area is very less as compared with the GO. So that's why we plan with the GO surface should be decorated with zirconium phosphate, because when the GO surface decorated with zirconium phosphate, it will become Geo also can able to give us a magnetic nature. That's why here we have achieved a better results. For after 120 hours, the corrosion has been very less, and also the corrosion is prolonged. So this is fire resistant with assist of limited oxygen index value. So in the case of WEP decorated, I mean incorporated with zirconium phosphate decorated GO is showing 31.25% limited oxygen. So when we compare with the other two, it is very good. So this is also because of the better arrangement and the interfacial interaction between the incorporated nanopillar and the WEP system. So this is the reinforcement mechanism for the anti-corrosion and also mechanical and thermal property analysis. So as I explained in the previously, so for the neat WEP, there are a lot of micropores due to evaporation, due to curing process. But while we incorporate GO into the WEP system, GO can able to make bond, but the arrangement between the WEP is not horizontal. So what will happen? It can make a zigzag path. But in the case of zirconium phosphate, it will make a horizontal layer, but though it has a very less surface area, so it is also can't able to withstand more time. But when we decorate our zirconium phosphate with the GO surface, what will happen? Generally, GO will become a large GO has large surface area. So while we decorated our zirconium phosphate on the surface of the GO, so GO also will become smegmatic in alignment. So it has a large surface area, so it can able to prolong the anti-corrosion time. And the mechanical and thermal property also because of this. When you see the image, you can easily understand the arrangement of the nanoparticles inside the WEP matrix system is the key reason, because here we are utilizing nanoparticles to enhance the polymer property. So if the polymer can able to achieve better property, means the incorporated nanofillers can able to make better bonding and also the better arrangement inside the matrix system. So this is my fourth project. This project is related to CNC. In this project we plan to work with the antimicrobial activities, but this project has not had been done completely. But we have synthesized the nanofillers, but the incorporation. Sorry. Hello.
Sir, your PPT is not visible, sir. Your PPT is not visible, sir.
Really?
Please share your PPT, sir. Yes, sir.
No, it is visible. You have to pick it up. It is visible.
Yeah, it's visible, sir. It's visible. It is visible.
It is visible, sir.
You continue. You continue.
You continue,
Okay,
sir.
so
Continue, sir.
So this is my fourth project, which has been worked with the CNC material, because CNC is having very good antimicrobial activity. So what we plan, so CNC alone, if we work, which will not make a better formation. Our major core is we want to work with graphene oxide. That's why we just decorated our geo surface with the CNC material here. So this project is also in situ process. So here after the nano filler synthesis, we scrutinized with XRD. So here we can see a 001 plane for GO, and for the CNC, the CNC has been prepared by ourselves. So we have got 1-101102000004 plane for CNC in the case of XRD. And while we go with the CNC decorated GO, we can see 001 peak also, which is related to GO peak, and also all other CNC peak also we have been achieved. So we can conclude that our geo surface has been partially decorated with our CNC material. And in the case of FTIR also, we can see that carbon peak and also the CNC peak is also there. So we conclude that the CNC has been successfully decorated with the geo surface. So Raman analysis, we can see the ID by IG value is increased as compared with the NIT geo. So we can conclude our geo surface has been successfully decorated with CNC. So in the case of TGA, so the thermal gravimetric analysis shows that when we decorated our CNC, as prepared CNC and as prepared GO all together, its thermal property is decreasing as compared with the NEAT GO. See here we can see the NEAT GO is showing around 38% residual value, But when we go with a neat GO, I mean CNC, neat CNC, it is showing around 20. But when go with the CNC decorated GO, it is around 36, 37 something. So
Excuse me,
I
sir.
think this.
Excuse me, sir.
Yes.
Sorry for the interruption.
Yeah.
PPT is not visible, sir. We can't understand anything.
No, sir, go to
Currently,
people, sir. Go to people.
Dear participants, go to people. There will be people, number of participants. From there, you can pin the presenter's name. There will be two names under Dr. Dhamodharan D. You have to pin the second one there. Or if you don't, if you couldn't view, you can go to YouTube session also. Or else that we have uploaded a video in our WhatsApp group in order to know how to pin the presentation. Sorry for the interruption, sir. So you can
shall I
continue.
continue?
Yes,
Okay.
sir, sure.
So in the case of XPS analysis, we have done with neat CNC, neat GO, and also CNC decorated GO also. So here also we can see the carbon peak has been reduced as compared with neat GO, and also there will be a small peak which is related to CNC peak. And morphology study has been done with the SAM analysis. Here we can see the GO sheet structures, the layer structures of the GO has been clearly achieved, and also the thick layers. But in the case of CNC, we can see the crystal structure. It doesn't have any proper structural arrangement, but we have got a needle shaped structure. Some in the TM analysis, we have got something like a plate structure. But in the case of CNC decorated GO, we can see the thin layer of GO decorated with CNC crystals. And here we can see CNC like a plate structure and graphene sheets, and also the CNC decorated graphene sheets for TM analysis. So moreover, the summary, what we plan, we conclude that we with the incorporation of some graphene or graphene oxide or surface modified graphene oxide can able to enhance the mechanical and thermal property of the waterborne epoxy polymers. So it is concluded that we can able to replace the solvent-borne epoxy polymers with the waterborne epoxy polymers to save our environment, because generally nowadays we all knew that our environment is facing a lot of issue because of so many problems are there. Even in that polymers utilization is also one of the important problem. So when we use solvent based polymers, in the initial I told you it will evaporate lot of volatile organic compounds, which is very dangerous to our environment, and also it is very dangerous to our human beings life. So with our findings, we conclude that we can, if we replace our solvent-based polymers with our waterborne epoxy, we can save our environment at least somewhat. So this is our summary, and I have some publications which my first project has published. Sorry? Huh? Hello? Hello? Sorry? Shall I continue?
Sir, no problem, sir. Please continue, sir. There are some interruptions. Sir, please continue, sir.
Continue, sir. Continue, sir.
Hello, and these are my publications. My first project has been published in Composites Part A, and second will be published has been published in Composites Part B. And some of my colleagues' project I just collaborated with some 3D printing work as well in my laboratory. And these are my publications. And thank you and questions.
Sir, thank you very much, sir. The presentation was so wonderful, sir. Very informative also.
Thank you.
So from your presentation, we could able to see the efforts what you have taken for reaching this level. So thank you once again, sir. Now the session is open for the participants. Dear participants, kindly unmute your mic and you can ask your queries to sir.
Yeah, I'm here.
This is Dinesh Babu from Rajiv Gandhi, Pondicherry. I would like to ask a clarification. Can we add graphene to polymer matrix composite by stirring alone without going for a sonication?
When we add graphene, what will happen generally, why we are work with graphene oxide because
Not able to hear you, sir.
So Dhamodharan sir, we are unable to hear you, sir. Dear participants, please stay back in the line. Probably there might be some issues.
Shyam? Mr. Shyamvel? Mr. Shyamvel?
Sir, I think he's calling the chief guest, sir. He's on a call with chief guest. I think he will connect.
Mr. Bharat?
Sir, he's making
Yeah,
call
what
to the
happened?
chief guest, sir.
What now?
Sir, chief guest actually left the meeting, I guess.
Okay.
Audio wasn't able to hear it. Yeah.
Sir, we'll wait for another few minutes, sir. Probably he might went out because of a small thing. 1 second.
Network issue.
Yes, sir. We'll call him, sir. Just in a minute, sir.
Okay. Please carry on, Shyam.
Please, sir. Please. Thank you. Dear participants, kindly stay back in the line, stay back in the meeting. Our coordinator has called sir, and very shortly he will join in the meeting.
Hello.
Hello, sir. Hello.
Sir, Dhamodharan, sir, welcome.
Yeah. Sorry, sir. It was a technical error. Sorry for the inconvenience.
Come again, sir.
Shall we continue? Yeah. Shall we continue?
Okay, sir. Thank you. Dear participants, again, the forum is open for your questions.
Good morning, sir.
Good morning, ma'am.
Very nice session, sir. I have one doubt. Is there any specific reason that you have quoted magnetic nanoparticles other than silver nanoparticles? Or how many available, sir?
Actually, the reason was magnetite nanoparticle have its own mechanical property as well. And also, you go with silver nanoparticles. Silver nanoparticles has very less mechanical property as compared with the mechanical magnetite nanoparticle. And also, the particle size of the magnetite nanoparticles is what we have used was high. And also, even magnetite nanoparticles is also having a agglomeration character, but here our industry people force us to work with magnetite because their application need magnetite nanoparticles. That's what we have gone with magnetite nanoparticle, because all our project is related to industrial work. So what they require, based on their requirement, we will work. So it
Yes.
is their requirement. So we gone through magnetic nanoparticles.
Okay, sir. Thank you, sir.
Sir, good afternoon,
Okay,
sir.
thank you.
Good afternoon, sir.
Yes, good afternoon. Good afternoon.
So you said that synthesis of waterborne graphene, sir. So you told that 10 degree we have to maintain ice bath. So is it possible in our existing laboratory?
No. Sorry, it is not waterborne. Actually, it is graphene oxide synthesis. Less than 5
Yes,
degree, because we can use ice bath.
Is it in the conventional laboratory we can do it, sir? Is it possible?
Yes, we can. If we are working with our laboratory, we can make with the laboratory scale. Actually, what we need to do while we perform this reaction, we need to work with fume wood. We should not make with atmospheric temperature. We should work with the fume wood.
Yes, sir,
And we should use ice bath. If we don't have ice bath, we can make some ice cubes. Then we can put it in the bath. Then we can make it as ice bath. We should maintain less than 5 degrees Celsius.
So how long? 10 hours, sir? Is it 10 hours for synthesis? You said.
Hello?
10 hours. 10 hours we have to maintain that one, sir, for reaction time.
Yes, 10 hours. 10 hours. For that case, we have one special equipment which was or we work with thermal conductivity analysis. Actually, we have one thermal conductivity instrument. In that instrument, we have one equipment which is connected with the ice bath. So in that ice bath, we just fix the round bottom flask. Then we just click. We just use that. Then we can fix the temperature even less than 12 degree in that instrument. So from that, we have achieved in this.
So
but I have no idea whether if you have those instruments, then you can also able to.
Thank you, sir. If you have any doubt regarding this, I can contact you, sir. Please hit me, sir.
Yeah, sure. Welcome.
Thank you, sir. Thank you very much.
Excuse me, sir. Excuse me,
yeah,
sir.
Sure. Yeah, tell me.
Sir, in the beginning of the presentation, you told that the graphene oxide is highly explosive. Then only you maintain the temperature below 500 degrees centigrade, sir. Is the graphene oxide is explosive?
No. Graphene oxide is not explosive. The synthesis process is explosive because of oxidation process. High temperature has been released. This is exothermic reaction. High exothermic reaction. That's why the explosive will happen.
During the synthesis of graphene, also is it possible to in explosion, sir?
No, it is not possible because graphene we no need to supply any oxygen functionalities on the surface of the sheet. During graphene oxide synthesis, we are going to supply some oxygen functionalities on the surface of the graphene. So during the functionalities supply, we need to give some oxygen functionalities. That's why we are doing here oxidation. If there is no oxidation, why? There is no need of KMNO4, there is no need of sulfuric acid, then there is no problem.
Okay, sir. Sir, another one question, sir. How do you conclude? How do we conclude that the intensity ratio is less than 1 or greater than 1 is how much defect on the prepared surface?
We can go with bed.
Hello, sir. I can't audible, sir.
We can go with bed for the surface area analysis.
Bet means
bet
what,
analysis. Bet analysis.
Bet analysis means, sir?
Bet analysis in the sense for the surface area determination equipment. It is analysis. I think in India we have. No, in Raman spectroscopy, we can conclude the structural defect. We cannot understand the surface area. For the surface area analysis, we need to go bit analysis.
I'm asking only the structural defects only, sir. I'm asking structural defects only.
Structural defect we can understand with the assist of
Sir, your voice is not audible for me, sir.
It will show us the thickness of the sheet, and it will show us the nanomaterial thickness, everything it will show with the atomic force microscopy, AFM. And also Raman also will show us the structural defect in the sense the sheet has been bulged or reduced like.
Sir, your voice is not audible for me. That's why I can't get you. So once again, sir, how do we calculate how many layers in our prepared sample? Hello, sir. Hello, sir. Sir, Dr. Sabri, sir.
Karthik sir, kindly wait in the line.
Okay, sir.
Dhamodharan sir, your voice is not audible, sir. Dhamodharan sir, your voice is not audible.
Samuel sir, actually,
Yes, sir.
our chief just left the meeting. Can you? He's joined. He's joining.
Yeah, he's joining now. Okay. Dhamodharan sir, can you hear me? Now your mic is in mute condition, sir. Kindly unmute and.
Can you hear me now?
Yes, sir.
Yes, sir.
Fine, sir. Fine, sir.
Yeah, you can able to find with AFM analysis, atomic force microscopy.
For how many layers present in our sample, sir? For AFM is enough,
yes,
sir?
Yeah, AFM is enough.
Some of the literature survey,
yeah, tell me.
Sir, some of the literature survey, I found that somebody using XRD to identify how many layers present in the sample. Somebody using Raman spectroscopy.
No, actually in XRD we can find the crystallinity. How much crystallinity it has. I mean, like interfacial interaction. Even in XRD we can find the d-spacing, but we could not find the layers. How many layers? I mean, d-spacing in the sense how much distance between the each adjacent layers.
One of the paper I saw, sir, during the increase of intensity, they determine this is 2 layer, 3 layer, 4 layer, 5 layer, like that. That's why I'm asking you, sir.
It is related to XRD. You know, expert software. Expert software.
I don't have, sir.
Yeah. In that expert software, you just want to fetch our XRD data. If you fetch our XRD data, it will show us which crystal structure your results having, and also it will show us the d-spacing, and also how many layers present in the sample. It will show in that expert software. It will not show in our XRD. In the XRD.
Sir, your voice
we can able to find with only XRD this one.
Sir, we can find where sir, we can get this values using Origin Pro.
Origin Pro we can't get.
Okay, sir.
We need to use expert software.
Spelling, sir.
Expert I score. EXPERT. Even you can
Expert?
check in Google, you can easily get expert.
Okay, well,
XXPERT, you can get easily. There is lot of pirated version.
okay, sir. Another one paper I saw, sir, that intensity ratio is less than 1 is that is few layer graphene, and intensity ratio is greater than 1 is called multi-layer graphene. How do you determine this?
Actually, it is not possible to get single layer graphene generally.
Okay. Okay, sir.
It is not possible. Even the initial graphene synthesis also, they found with that pair.
Sir, your voice is not audible for me, sir. This is very important question for me. That's why I'm asking, sir. Sabri, sir.
Sir, Karthik sir, Dhamodharan sir is in line, but I think he might have encountered with some network issues.
Yes, sir. இல்ல நீங்க இந்த क्वेश्चन அப்சர்வ் பண்ணிட்டு நீங்களே கேட்டு கூட இந்த ஆன்சர் கேட்டு சொல்லுங்க சார்.
சார் இல்ல நீங்க chat boxல இத ப்ரோசீட் பண்ணுங்க சார். We'll let him know in his WhatsApp, sir.
ஓகே சார், அப்படி இல்லைன்னாக்கா சாரோட கான்டாக்ட் டீடைல் மட்டும் கொடுக்க முடியுமா?
Sure, sir. We'll
Sir,
share
contact.
it in.
Sir, we will share it in the group, sir.
Okay,
Day
sir.
after tomorrow or tomorrow.
பண்ணுங்க சார்.
Once the FDP is finished, we will share all the expert mail IDs and mail IDs to contact them. Okay, sir. Maybe it will take a couple of days. Okay.
Okay, sir. Thank you very much, sir. Thank you, sir.
Okay. Okay, sir. Thank you, sir.
Dear participants, kindly bear with us. It seems that Dhamodharan sir has some network issues, so there's a little bit floating in his thing. You kindly please wait. Again, sir will join, and again we'll start the queries section.
Mr. Shamwell?
Sir, yes, sir. Can you hear me, sir? Sir, yes, sir.
Yes, Mahesh. Shall I leave the meeting or?
Sir, actually, sir has left the meeting, sir. I think he has some network issues, sir.
Okay,
Yes, sir. We'll contact him again, sir. And if there are no queries, we'll finish it with the vote of thanks, sir.
Okay.
Yes, sir.
Fine.
Hello?
Sir.
Sorry. It is due to internet problem because here some raining.
Dhamodharan, sir?
That's yes, sir.
Oh, okay. Sir, actually, I think there are some continuous network issues, sir.
Okay.
Shall we share your contact details with the participants so that those who have doubts can ask doubts via your contacts now, sir?
Sure,
Is it okay,
it's
sir?
okay. Yeah, I'm okay.
Okay, sir.
Okay.
Okay, dear participants. Okay, it's time to propose the vote of thanks. Once again, I thank Mr. Dhamodharan, sir, Dr. Dhamodharan sir, for his wonderful and informative presentation. Really, it is an entirely new era, as well as we came to know very important evaluation parameters from his research, as well as he also very kind enough to answer all our queries. So here already we have shared his contact details. So participants, if you have doubts, you kindly you can feel free to ask sir. And sir, really the presentation was so wonderful. We thoroughly enjoyed it. As well as I hope all the participants responded in a very positive way. So they are continuously congratulating and wishing you in the chat box. Thank you very much, sir. Thank you very much for your wonderful presentation, and thanks for your presence in our meeting also, sir. And also in this occasion, I like to thank our management, our trustee, and all the people in trust, and our CEO sir, then advisor sir, dean, everybody for giving us such a wonderful opportunity to arrange such kind of FDPs and meetings. And also, once again, I feel more prestigious in this moment to thank our beloved HOD sir, Dr. Sabrinathan sir, for continuously motivating us. And without his leadership, these things might have not came in such a wonderful and fruitful way. Once again, I thank him. And in this occasion, I would like to thank all the participants for their continuous encouragement and support. And even in our WhatsApp chat, we are getting uh, many positive ideas, as well as many positive encouraging things from the participants. We are really glad, and we are very fortunate to have such a wonderful participants. Thank you very much all. And last but not the least, I would like to thank all my colleagues for continuously supporting and lending their hands to make this FDP such a one in a such a wonderful way. Thank you all once again. And if we have any other queries, kindly, or if we need any other details, kindly ask us in the WhatsApp. We are ready to answer your questions. Thank you once again. Sir Dhamodharan sir, shall we wind up the meeting, sir?
Yeah, sure. Thank you.
Okay, sir. Thank you once again, sir.
Thank you.
Thank you, Dhamodharan sir. Thank you.
Thank you, sir. Thank you.
Sam, thank you for your thanks note. Dhamodharan sir.
Welcome, sir.
Sure, sir. We'll keep in
Thank you,
touch for the future program,
Yes.
as well as further research collaborations. Thank you, sir.
Yeah, sure. I hope so. Thank you.
Malay Reddy,
Sir.
thanks for introducing such a nice person for today's session. Thank you.
Thank you, sir. Okay, sir. Thank you, sir.
You only we identified Mr. Dhamodharan. So thank you for your courtesy extent. Thank you.
Thank you, sir.
Sir, again, today also we will wait for some more minutes, sir, for issuing the for giving the feedback form, sir. After 10 minutes, we will wind up the complete session, sir.
Yeah, fantastic, man.
Yes, yes, sir. Thank you, sir. Thank you very much, sir.
Participants, SAR's mail ID has been shared in WhatsApp group as well as here in the chat box also. So you have any queries, further queries, you please contact him. Thank you. Thank you one and all. For full session of this sessions of all the days FDP, you can join our YouTube channel so that you can find all the day sessions. And for today's session, here is the YouTube link. You can follow for the today's session. Thank you.
Sir, please share in the WhatsApp group also, sir.
Sure, Karthik sir, we'll do it.
Sir, you're asking regarding YouTube link or his contact details, sir? Karthi,
Both, sir. Both are
Yeah, sir.
share in WhatsApp group, sir.
Okay, sir. Thank you, sir. Thank you. Sure, sir.
Thank you, sir.